Good morning, everyone. Welcome to my presentation. I am MD Sofiul Alom from Ramajanipur Research Group, Department of Chemistry, University of Louisville. Today, I will discuss about electrocatalytic activity and pseudocapacitive charge storage of strontium, lanthanum, iron, cobalt series. At first, I will talk about the background of this study. Then I will show synthesis and characterization of these compounds, and then I will show you the electrical conductivity data, and then I will talk about the easier and OER electrocatalytic performance of these compounds. Finally, I will conclude it. Nowadays, 80% of the energy is coming from burning fossil fuel, and global energy demand is projected to reach up to 26 terawatt in 2040. Carbon dioxide emission is to reach 44 gigaton per year. To solve this problem, we need sustainable energy sources. For that, actually, energy conversion and storage devices are needed, which are actually like more efficient. For example, water electrolyzer, metal air batteries, solid oxide fuel cells, and so on. And let's see what's happening in the water electrolyzer. Here is the schematic diagram of water electrolyzer. In the water electrolyzer cathode, hydrogen evolution reaction is happening, and in the oxygen evolution reaction is happening at the anode. And to study these reactions, we need some we are looking for some parameters. For example, onset potential. Here is the onset potential. The onset potential is the potential beyond which, like after which the Faradic reaction started. And then we have over potential. Over potential is the potential actually that beyond thermodynamic potential, who is like, for example, for water electrolysis, thermodynamic potential is 1.23 volt. Any potential needed beyond that potential is called over potential. And to compare the results of different catalysts and different researchers, actually they are like, we are looking for over potential at a specific current density, that is 10 milliamp per centimeter square. For OER, you see here at 10 milliamp per centimeter square current density, the over potential, it has some value. Actually, we take this over potential at 10 milliamp per centimeter square to compare the result with the others. And another parameter is Tafel plot or Tafel slope, and we get this Tafel slot from this plot, and this plot, we get this plot actually from this curved region of this polarization curve. Now the problem is the HCR and OER reactions. This like the kinetics of these reactions are very sluggish or very slow, and to solve this problem we need like efficient catalyst which can like efficiently reduce the over potential. And researchers are working on these catalyst for this type of reactions, especially different types of oxide materials are like suitable for this catalysis. Today I will discuss about like one kind of layered oxides for this type of catalysis reactions, and that is let's see, layered oxides. Now let's see how the structure of this K2NiF4 type oxide. This is one kind of layered oxide, and in this layered oxide, it has general formula A2BO4, and here the A side cation is 9-fold coordinated, and the B side cation, you see here, it is 6-fold coordinated. And here the pink color ball, this is oxygen, and it has alternating rock salt and perovskite layer. Here you see these layers are called perovskite layer, and these layers are called rock salt layer. By changing A side and B side cation, we can tune the catalytic performance. That's why we choose like this type of oxide, so we can tune the catalytic performance to get the best catalyst. Now let's see how we synthesize and characterize these compounds. we synthesize these compounds via solid state synthesis method, and how, in this case, like we mixed all the precursor oxides and mix them together in a mortar and pestle, make a pellet and calcine it in like high temperature furnace, like at least 72 hours with intermediate grinding until we get the pure product. And we characterize these samples by powder XRD diffraction. Here you see the powder XRD diffraction of strontium lanthanum iron O4, strontium lanthanum cobalt iron O4, and strontium lanthanum cobalt O4. From this XRD refinement data, we see all the compounds are in pure crystalline phase with no impurity, and all of this has the same tetragonal I4 by MMM stage group. And from the aromatic titration, we see the oxygen content in strontium lanthanum cobalt compound is 3.78. That means it has like significant amount of oxygen vacancy, but other two, like it has like negligible amount of oxygen vacancy. It is almost stoichiometric. Here you see the conductivity data. Here you see the blue line, strontium lanthanum cobalt O4. It has the highest conductivity among this series, and on all of this showing semiconducting behavior. And this is the Arrhenius plot. Actually, from here we can calculate the activation energy. Here, this is the polarization curve of OER reaction, and this is the Tafel plot. And from here we can see strontium lanthanum cobalt O4, the blue line. It has the lowest over potential of 510 millivolt, and the Tafel slope of 109 millivolt. Actually, that means it is the best catalyst in this series, and we can explain this best performance by like easy orbital occupancy of strontium lanthanum cobalt O4. In this compound, the B side cation has easy orbital occupancy is close to 1, and from the literature we know if the B side cation has easy occupancy of close to 1 or 1, it shows the best OER performance. And here this cobalt has the easy occupancy of 1, and also this compound has the highest conductivity. Both of this is helping in oxygen evaluation reaction. For OER reaction, here is the polarization curve, and here is the Tafel plot, and here we can see strontium lanthanum cobalt O4 has the best ACR performance with an over potential of 337 millivolt, and the lowest here you see the lowest Tafel slope of strontium lanthanum cobalt O4 indicates the faster kinetics. And here you see the trend of catalytic activity in ACR is the same as the OER, so we can describe the same descriptor for AE or ACR and OER. A systematic trend is observed for conductivity and electrocatalytic activity, where strontium lanthanum iron cobalt has the best performance, and strontium lanthanum iron O4 has the lowest performance. And also strontium lanthanum cobalt O4, this compound has the oxygen vacancies, and based on this result we can say presence of oxygen vacancy and higher electrical conductivity facilitates the electrocatalytic activity. Finally, I would like to acknowledge my research advisor, Dr. Farshid Ramajanipur, on the left side, and second from the left side is Ram Krishna Huna, who is doing his who is a postdoctoral fellow in Ohio State University right now. And third one is me, and fourth then Amanda, Chandana, Kiniti, Chelom, and Surendra. And thank you everyone for your patience.